This will be one of a series of videos on rocketry and other science-related activities that are going on around Boys Ranch. This first video is on rocketry and rocket motors specifically. So you've built a model rocket. This happens to be called an apprentice rocket made by a company named Apogee. Once you've built the rocket, the next thing is to decide which size motor to place in the rocket. On the rocket plans, there typically is a list either on the front or the last page of the plans telling you which rocket motors you can use. For instance, this rocket can use a A83 up to a D107 motor. You would never use a D107 in this particular rocket because you would never see the rocket again. It would go so high. But anyway, they list it as a potential motor that you can use. There are various types of rocketry motors. These motors here are called single use, which means I put the motor inside of the rocket, I launch the rocket, I take this part out, throw it away, I'm done with it. This motor is called reloadable. This is a motor case. It's just an aluminum case. I take the fuel, which is housed inside of this plastic case, put the fuel inside the motor case, launch the rocket. Once the rocket returns, I take this part out, throw it away, and buy some more fuel. This is a little bit cheaper in the long run to do, and also it's always the larger size rocket motors are primarily reloadable. Some are single use, but most are reloadable motors. So let's talk about the different sizes. This is a A83, this is a C65, this is a D12.5, this is a E27W, this is a F56T, and this is a G4010W. This particular one, this J motor, it's a 658J357-17A motor. I know there are a lot of numbers. It's kind of confusing. So what does all that mean? We'll look at that in just a minute. Okay, we're going to use two charts that we have up to discuss the rocket motor sizes. For instance, we'll look at the C motor, which you can see in the left-hand chart. A, B, C, D, E, etc., all the way down to L. Those are motor classes. And for example, the C motor will have a motor that can produce 5.01 to 10 Newton seconds of force right here. And a Newton second equals 4.45 Newton seconds equals 1 pound. So you can see this C motor right here is capable of producing a little bit over 2 pounds of thrust. If we go to the right-hand side chart, we're going to look at a C64 motor. The C tells me the impulse, which is the class over here. So I know it's going to be between 5 and 10 Newton seconds of thrust. The average thrust is the next number, which is a 6. And there's something called a delay, and that is 4. And that's 4 seconds of delay time. So this particular motor is a C64. The motor I showed you in the previous video was a C65, which means instead of a 4-second delay, it had a 5-second delay. It produces the same amount of thrust. It's the same class motor. Now we'll look at the larger J motor. This is a motor made by a company called Cicerone. It's a J285. And again, we look over here on the right-hand chart. The left-hand chart. So we know its thrust total impulse is going to be 640 to 1,280 Newton seconds. It's going to fall into that range somewhere. So the total impulse of this motor is 648. So it's a very small J motor. It's just barely above that 640 entry number. It's 648 Newton seconds of thrust, of total impulse. That's the total amount of thrust the motor produces while it burns. You will see that this motor burns for approximately 2.3 seconds. It has an average thrust of 285, which is slightly larger than this. They do some averaging, so it's not always exact. But this is the average thrust, 285, but the actual number is 287. So it's a little bit off, but that's just the way it's done. And then you'll notice it has a peak thrust of 369. But notice that's just an N. There's no time associated with it. So for a very short period of time, just a few tenths of a second, it actually produces 369 newtons of thrust. On average, though, it produces 287 newtons of thrust. So that's how these motors are designated. Now, you notice I said this motor was a 648J285 17A. So that 17 is the delay. And that delay on this particular motor is adjustable. So I can make that delay anywhere from 1 second up to 17 seconds, 17 seconds being the maximum. And I'll explain to you in the next video why we use the delay and what the purpose of it is. Then we'll start looking at some videos of some rocket motors and see the good, the bad, and the ugly. So in the previous video we talked about the rocket motor sizes and the delay. So the reason we have a delay is once the rocket takes off and it reaches its highest point, which is called apogee, the rocket begins to arc over. At that highest point is when we want the nose cone to come off and the parachute to come out. So within these motors here, and also within the J motor, there is a delay charge. For example, the C65, 5 seconds after liftoff, there's a little black powder charge in the top of the motor right here. That charge will burn and pop off and it'll explode. It's a small explosion. And it'll pop off the nose cone, which allows the parachute to come out. So that's really critical for proper flight for the rocket. A couple of things that can happen with a improper delay. I won't put it back together just for the sake of time. But let's say it's a C63. They don't make one, but let's say they did. So 3 seconds after liftoff, this parachute is the nose cone is going to pop off. But if the rocket is still going up when the nose cone comes off, what can happen is the parachute can get torn up, or sometimes the parachute can get actually yanked off the rocket. The other side is, what if the delay is too long? So instead of a C65, let's say there's a C67. The rocket goes up, it reaches apogee, its highest point. The rocket begins to come down, it's building up speed. And because the delay is too long, the nose cone comes off, the parachute comes out. At that high speed, again, the parachute can get torn up, or sometimes the rocket actually can get torn up. So it's really critical with a rocket to have a proper delay charge set so the parachute comes out at the proper time. For the larger rockets, we actually use electronics to handle that because even though this is a C65, that delay actually might be 4 seconds, it might be 6 seconds. It's not exact. So it's going to be close. Sometimes it's a little bit long, just depending on how the chemicals were made and those types of things. With the electronics, we can get it exact. At the highest point, at the apogee, where it reaches its highest point, the electronics get it exactly right. We get the parachutes out at the proper timing. So that's the reason we have delays in rocketry. Next, we'll look at some videos of some rocket motors that perform well, some rocket motors that didn't perform so well, and actually what can happen to a rocket once a motor explodes inside of a rocket. So now we'll discuss how we get rocket motors burning. You might wonder, do we use a fuse? Do we light a match? What's the process to get the motor started? We actually use what's called an igniter. Here's an example of one. I'll get kind of to the side so you can see it a little bit better. This is called an E-match, an electric match. This is a small igniter. You'll see that little gray stuff on the top of the igniter. That's called pyrogen. It's just a chemical mix that burns. There's a nichrome wire underneath the pyrogen. When the wire heats up, it burns the chemicals and starts the chemicals to burn. This would be an igniter for a J or K size motor, maybe a small L motor. As you see, as the motors get larger, the igniters get larger. So this little D motor right here, I would take this igniter and insert it in the back of the motor, put a little clip to hold it in place, and this would get the motor burning. So I'm going to demonstrate to you what an igniter looks like when it burns. Normally we use a little control box like this, press the button, have a cable hooked up to the igniter. But in this case, since I'm here in the shop, I'm just going to use a little power supply that I have. So I'm going to set the igniter over here in the aluminum tray. Put one clamp from the power supply onto the igniter. I'm just going to give it a little countdown, 3, 2, 1. I'm going to touch the other clamp and you'll see the igniter burn. All right, 3, 2, 1. And that will get the motor started. A small D motor like I showed you. This E-match we would use on a larger motor. We would typically coat the inside of the fuel grain, which we'll talk about later, with a chemical to help this initiate the motor, being that it's small, but it's also very energetic. So I'm going to give a little countdown again, and if you will, just watch the E-match burn. 3, 2, 1. As you see, that's a little bit more energetic than the little D igniter. And this will be for a J motor. I'm going to kind of lay this one in the bottom because I know this one is going to be even more energetic. Hopefully we won't catch the shop on fire. Might get fired for that one, right? All right, so here we go. 3, 2, 1. Again, you'll notice this last one, when I said 1, I actually applied the power to the igniter, but it took a little bit longer for the wire to heat up. It took a little bit more energy to start the propellant to burn, or the power gen to burn. And so that's why you saw that little bit of delay between the time the electricity was applied to it versus these, which as soon as I touched them, these burned instantly, but this one had a slight delay. Anyway, that's how we get rocket motors started, and we'll look now at some videos of some motors burning. I'll explain the processes, and we'll look at some successful burns, some failure burns, and also some rockets that had some bad motors installed. When I did the igniter test, you may have noticed that the aluminum foil pan appeared to be burning, and actually what happened was we used this pan to mix a liquid sanding sealer, which is very flammable. And there was some residue left in the pan, and that's actually what started to burn. So it's not that the flame got so hot that the aluminum started to burn. Just wanted to clarify that. What you'll see next is some videos of some motor tests that I did with the A83 motor, a C65, and this is a H144 motor case. And these all burn successfully. You'll also see a 3-grain L motor, which is this one right here. That did not burn successfully, and I'll talk about that in the video. So you may be wondering, what is the largest motor we currently have at Boys Ranch? And it is a 7-grain N, as in Nancy, motor. This motor will produce around 660, 700 pounds of thrust for about 7 or 8 seconds. So it's a very powerful motor, capable of lifting a rocket to over 40,000 feet. So anyway, this is the largest one we currently have. But this is a N, as in Nancy, motor. All right, we'll look at some test videos, and we'll talk about what a successful motor burn looks like. This first test is a Estes A83 motor. You will notice the igniter wires are connected. The motor will start to burn. After 3 seconds, you will see the delay charge blow on the other side. So you'll see flame on one side, and after 3 seconds of burning, which is the delay time, you will see the ejection charge fire on the other side. Motor burn. Ejection charge fired. This will be a test of a Estes C65 motor. This motor is 4 times more powerful than the A that we just tested. So every time you go up a character in the alphabet, like from an A to a B, B is twice as powerful as an A, etc. This has a 5-second delay, so 5 seconds after the motor starts to burn, you will notice the delay charge on the other side. You'll also notice this motor burns a lot stronger. Again, it's a more powerful motor because it's 4 times the power of the A. So here we go. This is a test of a H144. A couple of things you will notice is as the motor begins to burn, initially there'll just be some gray smoke coming out of the motor case. That's because the igniter has burnt, but enough fuel isn't burning yet to fully pressurize the motor. Once it's fully pressurized, then you'll see the entire flame come out the back end, and the motor is actually burning fully at that point. And we've got two different views of it. This is a full speed, and then we'll look at a slow motion view. H144 in slow motion. The igniter has burnt. The fuel is starting to burn, but not enough has fully burned yet to pressurize the motor. More fuel is burning. Fully pressurized. Notice a nice symmetrical flame, very much under control. This is a test of a 3-grain L motor that did not go well. When we do these tests, especially with the larger motors, we're typically 100 to 200 feet away. Even a larger motor, we might be a little bit farther away just for safety reasons. The nozzle in this motor is made of graphite, which is relatively soft. I mean, you can put your fingernail impression in the graphite if you press hard enough. Because the graphite is traveling at such a high rate of speed, when the motor explodes, you'll notice there's an aluminum bar across the top of the test stand. That bar is going to get blown off by the graphite nozzle. Again, this soft graphite traveling at a high rate of speed has enough energy to break this aluminum bar off the motor test stand. You'll also notice the flame of this motor is not uniform. It starts to change shape, which is an indication that something is happening to the fuel. As the motor begins to overpressurize, the shape starts to change, and then there's an explosion. People were over on the Magenta property across the highway, and they actually heard the motor let go because the noise was so great. So here we go with L motor not doing so well. These next videos will just show you what happens when a large motor lets go or has a CATO, catastrophic failure, and the damage it can do not only to the rocket but starting fires and those types of things. Most of these videos I personally witnessed, or actually this one that you're seeing right now, I did take the video of the rocket. Also be aware that we're at a safe distance from these larger rockets. Even though in the video it looks like we're fairly close, we're actually 1,000 feet away from this rocket for safety reasons. And based on the size of the rocket motor, there are distances that we maintain as far as safety margins away from the rocket, just for our own safety. So here we go. There'll be several of these videos. The last video will be a rocket that has a camera that we launched over on the Magenta property that flew well. It didn't have any problems, but I just thought you might like to enjoy it. So here we go with some live rocket videos.
Okay, we got Rick Van Voorhees launching his Nike. Estimated altitude 13,000, and we're going in 5, 4, 3, 2, 1. Oh! All right. All right, on the far pad we got a N1885, something like that. It's big. Okay, we're going to arm the pad. Okay, pad is hot. And I'm going in 5, 4, 3, 2, 1.
Let's go, guys. Fire!
That particular rocket was built by a university south of Canyon. I won't mention any names. And that was launched at our, where we used to launch at our Wayside launch site. This next video, I just want you to see the size of this motor. It's a P, so it's a 6-inch diameter. It looks to be about a 4 to 5 foot long motor that is going in this rocket. It's an extremely powerful motor. And again, things don't go so well. So anyway, you'll get to see a little bit of the setup of the rocket itself, and then the how things go wrong.
Rattle it and push forward. Keep holding from the back end. It's going to want it. And you got to get it lined up perfectly. I'm just supporting you.
Yeah, let go of it. Out the way, out the way. Ready?
It has expanded, hasn't it?
Ready? 1, 2, 3.
Turn it. You gotta hold back. Go ahead. Oh, sorry. You gotta get a good running start on it. Yeah. Yeah, one of those. One out. Kind of hold it as it goes up. You want to raise it?
We're definitely going to have to hold the fins to keep it from rotating. Just going to get away from it. You have a career in this.
Okay, we're going to need the big ladder.
12,000, total impulse 50,000 newton seconds. Average thrust is 12,000. Burn time is 4.5 seconds. Flying on what they call a Blue 22. We got a 28-foot sky angle chute. Protection is in its device type, so I'm getting a little nervous here. It says thermal regular. I'm going to get underneath this table and we're going to go in 10, 9, 8, 7, 6, 5, 4, 3, 2, 1.
Okay, 156, huh?
238.
For guys, bummer, sorry.
Okay, 156, huh?
238.
For guys, bummer, sorry.
Let her burn. Let her burn. There's nothing out there to burn. Just let her sit there.
This is a rocket we built a few years back that we launched on the Magenta property. We put a camera in the rocket. Fortunately, this is a good launch. We don't have any problems with the rocket. Just thought you might enjoy the video. The noises you will hear are the electronics.